Compound events. Well, today what we're going to be looking at is kind of like intersection and union style problems. You've seen like Venn diagrams in the past. We use those a little bit with these compound events to talk about whether or not something is mutually exclusive and so on. Excuse me. So what we're going to do today is we're going to look at some very simplistic unions and intersections. And I'm assuming you guys have all worked with Venn diagrams, a union or an intersection of this before, probably in a science class I'm going to go out on a limb on. Do you guys know what it means to be mutually exclusive? What's going to happen here is we're talking about what are called compound events. There's two events happening. Two events can be, they can intersect, they can overlap, they could have nothing in common. So what we're looking at here are some very easy examples to talk about. Something that's called mutually exclusive. When something is mutually exclusive, it means that there is nothing in common between the two events. Okay. There's nothing in common.
So you have to do like when A equals 5 over 9, while B equals 4 over 9, for example?
Something like that, yeah, something along those lines. And when we get into this a little bit more today, you'll see how very simple this stuff works out to be. What we're going to talk about is how we work with this probability and how they write it. They talk about probability with the letter P. When you guys were taking that test last Thursday and Friday, there were some things that came up with the probabilities when they were talking about some events. I think some people had asked me about, there was like a P prime. Did you guys see this symbol at some point?
What the heck was that? I did not.
Or some event? We're going to talk about that today. So what we're looking at here today is we're going to talk about the probability of A or B occurring in a couple of different ways. Okay. Now, one of the ways it's going to work out is if something is mutually exclusive, means there is nothing overlap. And I've got a really easy example to deal with cards to show you how this works. So let's say that we have a deck of cards. And I want to find what would be the probability of getting a heart or a diamond.
It would be 13 on each side.
1/2. Those are two independent events. They share nothing in common. So if I want to figure out what the probability of getting a heart or diamond, if I want to figure out the probability of a heart or a diamond, there's no heart and diamond card, correct? That would be considered, so this probability would be mutually exclusive. There's no overlap. So what you wind up with is the probability of a heart plus the probability of the diamond. Well, how many hearts are in a deck of cards?
13.
13.
Wait, what's going on?
How many hearts?
13 out of 52 plus 13 out of 52, which gives you the 26 out of 52, which is 1/2. So the probability of drawing a heart or a diamond is 1/2. They're completely exclusive of one another.
Hey.
And I win. Okay?
I did the school, not the house.
True. Okay.
But
The difference now becomes-
is one that they share together, like heart, diamond, hybrid.
Well,
Well, technically, you could say probability of getting red.
that's true. You could say that. Now, the other one is a little bit different. See if you can figure out the difference in the wordings here. What would the probability, how would I write out the probability of getting a 3 or a spade?
Well, there's a 3 in spade.
See how that's said a little bit different? The probability of a 3,
352 plus 1.
or a spade. Well, think about what there is. How many 3s are in that cards? 4. There's 4 of them. There's 4 out of 52. How many spades are in a deck of cards?
13.
There's 13 out of 52.
But there's 1 3 in the space.
So what do I do to
Divide
that?
by 152.
Subtract out the 1. You subtract out what they have in common. So when it's not mutually exclusive, when there's something they have shared in common, we subtract out that what's called intersection. What they have in common, the probability of A and B. This is mutually is the one that you don't have to worry about subtracting anything out. They're completely, they can happen on their own. When there's something that has that overlap order, a 3 and a spade, a 3 or a spade, or it is a 3 of spades. So in this case here, you wind up with, well, (16 out of 52, otherwise known as 8 out of 26.
Could you say P of C? This is the probability of getting a 3 spade, which is an event all on its own.
What was that?
For the equation up there, could you
Yeah.
say it's P of C?
No, because you can have more than one event, right? I'm just trying to make this simple, okay? When we're talking about these things, you get into statistics like this, a lot of times they're gonna write it a little bit, just a little bit differently than what we have here. You will see, have you guys ever seen it written with, when you've done Venn diagrams with a U? Have you ever seen it written like that before? Like probability of A, B, or A. You ever seen it written like that before? Okay, I'm not gonna bother with it. Sometimes you can see that if you guys have worked with some Venn diagrams before. It's a shorthand way of writing it out. It's the word and or too many letters. Yes, sir?
Why is he subtracting 1?
What's the overlap? If you think about when you have a deck of cards, if you have, there's 4 3s, you know, you have 3 of hearts, 3 of, there's 4 of those, there's 4 3s, but then in the spades, there's 13. But one of them is sharing in within both sides. So I double counted it to back it out. Okay. Now, sometimes this book, just to get you in the habit of what you're solving for, is it, did you bring your own cards today? Nice. So in this case here, it wants to find out what the probability of A and B is. So is this a mutually exclusive problem or a non-mutually exclusive?
It's a non.
It's a non because it has A and B in it. So what this book does is sometimes they will write it out and they'll give you a bunch of stuff. Well, probability of A or B is the probability of A plus the probability of B, subtract out the intersection. It's the exact same problem we just did with the 3s or a spade. But they're giving you all the different probabilities. You just solve for the missing part. A or B is 0.8, is 0.7 plus 0.2. What are we missing here?
The overlap.
Yeah, so how do I solve for that simple one-step equation?
Minus 0.1.
Minus 0.1. Everybody see that?
Wouldn't that be and?
Yeah.
A or A and B?
Yeah, it's right here.
But like on the bottom, equals 0.8.
No, it's right here. Point A or B is 0.8. So that's where it starts out. Remember, the formula itself is the A or B's. Okay. So this is so you wind up with a very simplistic one-step equation that most of you will probably be able to solve in your head. Okay. Drop the cards. All right. So, what's the the probability, you guys can guess, this has nothing to do with what we have, I just dropped 2 cards. I will give,
Extra credit?
I will think I'll give a bonus point if somebody guesses the 2 cards. Well, we'll figure something out. Write down what you think they are.
A spade and a heart.
Wait, like the exact.
The exact cards.
Oh, we have
I
to
just dropped jerk.
Hey man, it's not
That was funny.
1 second.
This is rigged.
This is rigged, yeah. All right, so what's your probability that you can get an ace or a face card? Ace or a face card?
Ace or a
Wait,
face card? You're not gonna use that as a face card?
No, they're ace or a face card. Now, face cards are going to be what?
Kings,
Jack,
queens,
king,
jacks.
King, queens, and jacks, okay? So the probability of an ace or a face card. Is this mutually exclusive or is there an overlap? It's mutually exclusive, okay?
Well, it says right there.
Well, yeah.
Yeah.
How many aces are there?
4.
How many other face cards are there?
3.
There's 12, yeah, 3 face cards times 4, you get 12. So the probability that you're going to get an ace or a face card would be 16 out of 52.
4 over 13.
It's not really good percentages there, is it?
Not really.
I can't shuffle. I don't play board.
It's
So we're even. I'm winning. 2 out of 3 I win.
oh, come on, Tyler. You're disgracing my deck here.
Okay?
I want to.
Try this one then. What's the probability the card is a heart or a face card? Again, they're calling face cards kings, queens, and jacks. Heart or a face card? You gotta worry about that. No. Can you have a probability greater than 1?
Fraction,
Yeah,
we
me
have
too.
to simplify.
Okay, well, you
11
know
out
you
of
can't have
26.
one one.
No, I don't.
It's 11 out of 26. It doesn't have a 22 anymore.
Does this one make sense where you have to back something out?
Yeah.
You have 13 hearts. How many face cards were there again?
12.
There's 12 out of 52 there. But of that 12, what do we have to subtract out?
1 is 3 over 52.
We gotta, yeah, to subtract out 3 of the hearts you've already counted. So it's 22 out of 52. 11 out of 26. So the probability that we can flip over a card that is a heart or a face card is, yeah! I'm very happy sometimes. Yes, sir.
Do I still get my board?
No, cheater.
We need
You never said we couldn't.
No, I didn't see it.
You saw it.
it.
You know what? You chose the other one to make it look
I
like you
could've
didn't see it. Cheater.
I guessed with the ace.
Okay. Now's where it gets a little bit more interesting. Last year, a company paid overtime wages or hired temporary help during 9 months. Overtime wages were paid during 7 months, and temporary help was hired during 4 months. At the end of the year, auditor examines the accounting records and randomly selects 1 month to check the company's payroll. What is the probability that the auditor will select a month in which the company paid overtime wages and hired temporary help? So right off the bat, we're looking at working with the second one, the non-mutually exclusive. Everybody see that? Because they're asking us to find out the and part. Where was that overlap? We're trying to figure out the overlap. So what happens in this case, they're giving you some information. We know that, excuse me, the probability of the overtime or the temp help happened in 9 out of 12 months. Told you that right there. How many months are
Once
there?
in a year.
I told you.
It's one six, so it's like, that, and you start
It tells you that the overtime, the probability of overtime,
now.
was paid 7 out of 12 months. And the temp help
So you make 7 over 12 plus.
was 4 out of
over
12.
12 equal 9 over 12. And then you kind of need to do this, then you need to minus 1/6.
Everybody see where this is leading? You're setting it up. I've heard people say the answer a couple of times here. You're setting it up right off with just the given information. We know that the 9 out of 12 is going to equal the 7 out of 12 plus the 4 out of 12 minus
1/6.
something.
1/6.
So you can do a couple of things. Move this over here, move this over here, and everybody's mumbling out here at 1/6. Okay. What's winding up working with here are these just very straightforward formulas. Okay. It looks like it's going to be awful, but it's once again, it's a one-step setup. Okay. We're not having to do any of the real calculations yet. Here's what the world that Klein system meant. It means a compliment. It doesn't mean you look very nice today. It means the opposite of something.
You know.
That's rude. What
So-
are the chances of that happening?
It's funny. So the complement of something prime. Well, what is the probabilities are always between 1 and 0. The complement is just 1 minus the regular probability. So if we had the probability of getting a heart,
The probability of not getting
the
hurt.
probability of not a heart, well, what's the probability of a heart?
13 out of 52, so you take
13 out of 52. This would be 1 minus 13 out of 52. Wouldn't that be the same thing as going 13 out of 52 plus 13 out of 52 plus 13 out of 52 to get the other decks or the other suits?
Yeah.
It's the same idea. What happens with using complements makes some of these probability of the events a little bit easier to work with.
13
All right, it's a little bit quicker to calculate some of them.
39 out of 50.
Why do we need the 5?
It's just called a complement. It makes solving some of these problems a little bit easier. And then it works out a lot of times with dice rolls. Okay, it works out a lot with that. So let me show you an example with dice. Using complements here, what I have up there is just all 36 possible rolls when you roll a pair of dice. Is it a pair of dice or a pair of dice?
Paradox.
It's bias.
I know, but when you say if you have a pair of dice,
Yeah, you do, you have some of it or food. Right.
this is why I teach math. Me fail English. So what they're saying here is the sum is not 8. So if you want to find the probability of the sum not 8, well, find the ones that have the sum of 8 and subtract it from 1. So how many of these give you a sum of 8? Well, let's see, here's 1, 2, 3, 4, 5. So there's 5 of them that give you the sum of 8. So it would be 1 minus 5 out of 36. What we're doing here is just quicker to do the calculations using complements. Yeah.
Say we didn't have that kind of like that whole diagram and all of that, we have to figure that out.
Okay.
How do you use?
It's very simple.
Yeah.
It's just the numbers 1 through 6. Okay. The sum is greater than or equal to 4. So the probability
So you do
that the
one.
sum, is greater than or equal to 4. So if I want to find the sum is greater than or equal to 4, well, I start by figuring out where does it equal to 4. It starts here. So how many of them are not?
3 over 36, so 1 minus 2.
Very good. Everybody see that? It's just a little bit quicker to work with complements sometimes. Since there's only 3 of them that are not going to be, we look at the less than 4. So there's 1, 2, 3. So we say 1 minus 3 out of 36. Working with complements is just quicker. Okay? It's just a little bit quicker to work with. Okay? Yes, sir.
Wait, it says greater than also.
Greater than or equal to? Yeah. This starts here at greater than or equal to, so here's 4, 4, 4. There's only 3 of them that are not.
Oh, yeah, it's the.
Yeah. So I'm looking at the ones that are not and just subtracting it out.
Okay.
It just makes, like I said, just makes calculations a lot quicker. That's all. Okay? Give you some try it. Okay?
Hey, Mr. Murphy.
Yes, sir.
Two ships in a harbor.
2 ships in a harbor?
Yes.
I don't know.
A paradox.
Oh,
Think about it. They're in dock.
Josh, definitely.
Right.
2 ships, a pair, a pair. Two
Yeah, how did the
ships.
ships become docks?
2 ships in a harbor.
Uh-huh.
So how many docks would you need to dock 2 ships?
What if the ships were docked next to each other? You ever seen 2 ships moored together? I'm getting nautical on you.
There's a flaw in this.
Yes, there is.